Hello and welcome again to my Physics Online video lecture series. Today's video we're going to be talking about what happens when we break the sound barrier. We're talking about sonic booms today. We'll be talking about the Mach number and the Mach angle as well. So let's get into that a little bit. Before we do, let's begin by recalling something from our last video. The last video, which you should have watched right before this one, is about Doppler shifts. So the Doppler shift basically had an equation to describe the detected Doppler frequency, F Doppler, and it depended on the sort of native or natural emitted frequency F0. It depended upon the speed of the wave in the medium. It depended upon whether the observer was moving towards or away from the source, and it also depended upon whether or not the source was moving towards or away from the observer. And so this was the basic equation. I want to focus on just part of this. So let's say a stationary observer, and that's stationary relative to the medium that the waves are being carried through, by the way, and source moving towards. And the reason why I want to look at just this is because it simplifies this equation a bit to a point that I want to highlight, which is that in these conditions, the Doppler shifted frequency is sort of this native frequency times the speed of the wave, that's a positive number, divided by the speed of the wave, again a positive number, minus, and the speed of the observer is itself a positive number. So positive, 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 there's a subtraction here, and we might ask, what if V wave equals V source? And for that matter, what if V wave is less than V source? Well, in this thing's case, you have division by 0. So obviously bad things happen when you try to do that in your calculator. And in this thing's case, you don't have division by 0, you do have a number, but you end up with a negative number here, and so you end up with FD is negative. And so somehow you have a negative frequency, and physically this is not defined. What does a negative frequency mean? What does it mean for a negative number of waves to arrive every second? So that's where today's lecture basically comes into play, is what happens if either of these things occur? This one mathematically not well defined, this one physically not well defined. And the answer is that you basically break the sound barrier. You get sonic booms, and you could think of this as, what if I have a source? And here's my source, and that source is emitting waves. Okay, so every, whatever, 5 waves a second or 500 waves a second or what have you. The waves are basically centered on the source, and they are all equal distant from each other. So this is like your stationary source. So if I put observers all around this source, maybe one here, one here, one here, they all hear the same thing. So this is stationary. Now, if the source is moving, so moving source, let's say that the source starts off right here, but it's moved over to right here at a given time. Okay, well, maybe it's emitting within its own reference frame the same set of waves as it does over here. Okay, so that means that I should have a wave like this. Oops, that's maybe a little big. A wave like this that is immediately surrounding the source. This is the most recent wave that's been emitted. Okay, but when did it emit the previous wave? Well, it was probably about right here when that last wave was emitted. And so rather than being a circle centered on this dot here, our previous wave, if we were to draw it out, is really centered, if I can move it, right here on this little point. Okay, well that's not so bad, right? Where was the last wave before that? Well, the last wave before that was a little bit bigger still, maybe like this. But that last wave wasn't centered on this point here. It was centered maybe on this point here, where this guy was when this wave was emitted. So we got to move this thing over, and that's centered about there. I don't know why it decided that it's now attached to the words moving source, and so on. Okay, and then the previous wave to that maybe is actually centered on this little guy, and the previous to that is centered on this little guy. So I have another wave, maybe that's this, and then another wave that's over here, this. And those are centered on each consecutive X. And we could even maybe like number them. So this is like 1, 1, 2, 2, 3, 3. This is number 4. This is number 4. This is number 5. This is number 5. Over here, 1, 2, 3, 4. Oops, sorry, I'm numbering them backwards though. It should be 5, 4, 3, 2. One more in order to make it the same number of waves as I showed. So 1 is over here. They're all centered on the same point. Okay, so again, this doesn't cause a problem in and of itself. Although if the source is moving at the same speed as the waves are, then they sort of build up a little front here to where the front edge are all in the same location, and that's basically building a really strong pressure front, and that's where you get your sonic booms from. Okay, now what if the source is moving really fast? Okay, so what if the source is moving like this, so that it's very far spaced relative to the waves that it's trying to emit? Well, my first wave again is this big like this. My second wave should be a little bit bigger still, maybe like this. Oops, see, I'm making these too big. It's hard to be consistent when hand drawing. First wave, second wave. But again, the second wave here is actually centered not here, but over on number 4, like this. Don't know why it's being so difficult to move. Okay. My next wave, my third wave, the one that was emitted prior to wave number 4, is going to be centered on point number 3 over here. My second wave, the one that was emitted prior to this one, should be centered on point number 2. So I should be able to move this guy over to here. And then my first wave is going to be centered on point number 1. And there's a little bit of a misdrawing going on here, because if this thing is truly moving faster than the speed of sound, then the wave fronts shouldn't catch up with the next point ever. So this one maybe is a little bit too big still, and I need to just move it like this. See, now it hasn't caught up with point number 3. Point number 1 can't have caught up with point number 2. Draw. That's kind of a circle, right? free drawing is not going to cut it for this next point. I'm going to have to borrow a diagram that somebody else has drawn, which is this little diagram that comes out of OpenStax. And the point behind this diagram, again, you can see this is moving roughly right at the speed of sound, maybe slightly faster, because each circle is just barely making it to the next dot upon emission of the next wave. And the thing is that you have sort of this cone that's made. In 2 dimensions it looks like an angle or a triangle, and this is essentially your Mach cone. This angle right here, 2 theta, or more appropriately theta, is called the Mach angle. And if you're looking at this, essentially what these red lines represent is sort of the wavefront created by all of these waves together. And so this wavefront is propagating like this and like this. This is your actual sonic boom that you hear if you have like a supersonic jet flying overhead. So this is your sonic boom wavefront. And it turns out that this angle, if I take just this part right here and call it theta, I can see that along this axis and along this axis of a right triangle that I could draw like so, along these 2 axes I basically have speed of my wave and speed of my wave source. And again, the relationship between them is that the sine of theta is equal to the speed of the wave divided by the speed of the source. So this is what's called the Mach angle. And for what it's worth, it applies not only to sound waves, but to any mechanical wave. So if you have a boat that's moving on water faster than what a wave on water would travel, you have a sort of visible shock wave that goes with that boat. There's actually 2, one from the bow and one from the stern, but they're called bow shocks. So one is from the front edge of the boat and one's from the back edge of the boat. And those are the equivalent for a boat on water to sonic booms for a supersonic object like a jet or the end of a whip. If you hear like somebody take a bullwhip and crack it, that cracking is a small sonic boom that the edge of the whip is making. But those are these shock fronts. And so this is your Mach angle. And basically your Mach number is giving you the ratio of these 2 things. So if you have somebody who's traveling at Mach 3, it means they're traveling 3 times the speed of sound within that medium. And I think that's it for today's video. Hopefully you've learned a bit from it. It should be obvious, I should add, that this Mach angle is getting smaller and smaller the faster the source is moving. So a small Mach angle means a large Mach number. But that's it. Thanks for watching.